Good afternoon, everyone. My name is Carter, and this is Step 1, 1924, Question 1. Okay, so let's get straight into this, right? So my house has an attic consisting of a horizontal rectangular base of length 2q and breadth 2p. And we're given that also p is less than q, and the attic also consists of four plane roof sections, each at an angle theta to the horizontal. Okay, actually, let's just pause there and just make sure that we understand what's going on here. So effectively, we have sort of our roof or our attic, um, looking like looking like these diagrams. The diagram on the right I kind of just plucked from the student room, but the diagram on the left was my attempt at drawing it. Effectively, we can see that on the right, well, I'd say definitely have a look at the right one first, because that's probably a lot easier to visualize sort of the situation with. But you can see that we effectively have sort of this rectangle here, and that's our base, and that rectangle obviously has length 2p and length 2q and breadth 2p. And then we have these sort of four plane roof sections. So some of them are like triangles and some of them are like trapeziums. And effectively, the two trapeziums, they meet along this sort of common line, which has length r. And the two triangles meet at sort of opposite points on that common line. Okay, so you have those four plane roof sections. So there's sort of two triangles. So that's one and that's two. And then the two trapeziums, so that's sort of like one, and that there is two. And each of these is inclined an angle theta to the horizontal, right? So I think that's best described by this triangle here. So if I just take one of my faces, so my triangular plane section or plane roof face, then you can see that effectively this length here is like the height from the ground to that ridge, so to that common point with length r, a common line with length r. So we can call that height h, and we have this sort of length here, which we don't know, is just x. But then we can see that that angle theta is effectively the angle at which that triangle is, sorry, that's horrible, is inclined to that sort of ground level, to that horizontal base. And that has to be theta. And so I could put that triangle in any four of these plane roof faces, and the angle made with the horizontal or with the base should always be theta in this setup. Okay, that's actually more important than you might think when answering this question. You might even gloss over that fact, but it is actually quite an important one, and we'll discuss why in a bit. Okay, so effectively, now that we understand what's going on, we need to now show that the length of the roof ridge is independent of theta. So effectively, we want to find an expression for the length of r, which might seem a little daunting, because I mean, it's clearly not going to be like a numerical answer. It's not going to be like 4 centimeters or something. It's going to be in terms of probably p and q, right? So, and maybe even some theta, right? So, well, hopefully not a theta, because it needs to be independent of theta. But how do we show that? And the way to go about this is to have a think about specifically these two triangles that the person on the right has sort of drawn in their setup. So we have one triangle here, right? And we have another triangle here. Okay, so there are some facts about these two triangles that we need to know. And the first one is that this length here, so if I were to just sort of walk sort of from this sort of line of length 2q sort of just vertically upwards, at least on this diagram, or just like forwards, then you would have to walk this sort of length p to get directly below that ridge r, the ridge with length r that we care about, right? So this length here we know is p, okay, which is exactly half of our breadth, right? So why is that? And the reason why it is simply because we needed all four of our plane sections to be at an angle theta to the ground, which means that if I tried to move this ridge anywhere like sort of upwards, so if I moved it there and I tried to connect all the sort of ends of the roof together, then my angle made with the ground would definitely not be theta everywhere, okay? And the same obviously if I move it back. And if I even like perturb it a little bit in any direction, the angle theta will not be sort of uniform throughout the roof. So the problem is simply in that we need theta to be the same everywhere. And we cannot guarantee that unless we have this symmetric configuration. Okay, when I say symmetric, all I mean is that effectively the length from sort of this bottom line here to the point directly below the ridge has to be half of the breadth, and the width, or I guess whatever, from the sort of left side here to that point R has to be the same as the length or the width, whatever you want to call it, from the right end of the rectangular base to the point where you're directly under R. So these two lengths here need to be the same, and these two lengths here need to, and this length P, this length here from the ground to the point where you're directly below R needs to be half of the breadth, which we know is 2P, so that has to be P. Right, so we have this sort of symmetry to the problem, which pretty much makes it pretty nice to solve. But how are we actually going to solve it? Well, again, we need to just consider these two triangles here specifically. Now that we know sort of that this length is P, well, what else do we know? Well, we can label this height here H. So obviously when I'm standing directly below my ridge, the question is how high would I have to sort of move? What height would I have to sort of jump or whatever, be transported? What length would I have to sort of go up to get to the point where I'm standing on the ridge, if you know what I mean. So if I'm standing on the ground in my attic, how high would I need to be transported and to the point where I'm standing directly on top of the ridge is the question. And obviously we don't know. We're going to label that height or that sort of length as h. Effectively, it's just the height from the ground to the top of the ridge. I don't know why I overcomplicated it there. But we just label that as h. And then what we also know, the last piece of information, which is pretty much crucial, is, well, obviously we also know these are theta, right? But that should already be given in the diagram. Well, you should already have seen that. But we also need to know that these two angles here are both 90 degrees. The reason for this is pretty much simple. Obviously, the height is directly vertical, right? Whenever you have a height, you're basically just standing at a point and you're moving directly vertically upwards, or at least in this case, we've labeled the height as such. So it's effectively just you're standing underneath the ridge, you look vertically upwards, and supposing that you could somehow fly upwards or something, you would fly height h to the point where you're standing on top of the ridge, right? So obviously height h is just like a vertical distance, if you will, right? It's not horizontal at all. And it's definitely not like angled in any direction. It's just a vertical distance. And obviously our length x is just a horizontal distance, right? Since our entire plane is just horizontal. If we move anywhere in the plane, effectively we're just sort of moving, or at least in this case we're moving horizontally, right? Obviously if you move sort of like upwards, then you're moving vertically within that plane. But in this case you can clearly see that no matter where I move in that plane, I'll always be perpendicular to that vertical height h, right? Because it's literally just extending out of the plane directly upwards, right? So it's not an angle to the plane, effectively. So we know that those two lengths, h and x, or those two sides with lengths h and x, are perpendicular, and the same is true for the sides with length h and p. Okay, so obviously if we consider those triangles, so obviously you want to find the length of the roof ridge. So if we consider those two triangles, so consider the triangle below. So it's going to look something like this, this, right? So this is obviously 90 degrees that we're talking about. This is our theta, this is our length x, and this is our length h. So we can clearly see, we see that tan theta is obviously h over x. So we can obviously rearrange that. As I just clocked that I'm not showing this. We can obviously rearrange that to have that h is equal to x tan theta. So that's the first piece of important information. So that's our sort of our triangle one. I'll just say triangles below because I'm going to add another triangle. So triangles below. And then our second triangle is going to be something like this. So let me just draw that out. Come on. There we go. There we kind of go. Okay, nice. And so obviously we have that this angle here is 90 degrees, the same angle as theta, but in this case we have this length is p, and this length here is h. Clearly in that case we see that tan theta is equal to h over p, right? Which implies obviously that h is equal to p tan theta, which we already know is equal to x tan theta. So we can technically divide both sides by tan theta, as long as tan theta isn't 0, because you can't divide by 0. But if it was 0, then theta would have to be 0, because tan of 0 is 0, which wouldn't make any sense. You can't have a roof where the plane sections are all just like lying flat on the roof. It's kind of just not like there's no attic anymore, right? It's just there's no room, there's no volume. It's just degenerate effectively. The same is true, obviously, if theta is equal to pi radians, so 180 degrees. Obviously then, tan of pi, tan of 180, they're both 0. But the problem is that, again, you're having this degenerate case, right? The sort of plane sections are now 180 degrees to the horizontal, which just means that effectively you have no attic. It's just like, it's just degenerate, right? And it's very easy to find the volume of the attic in that case, right? It's just 0. So those two cases are degenerate and they don't really matter. So we can divide by tan theta to get that p is equal to x, right? Since we know that tan theta is not going to be equal to 0. Once we have that p is equal to x, the remainder of the problem becomes pretty simple, because obviously by the symmetry, we can just relabel these x's as p's. And then we can see that this entire length here would be 2q. So this entire length here should be 2q, right? Because effectively it's just some length from the left-hand side to the right-hand side, walking like without changing the angle at which you're walking. So if I walk from the left-hand side of that roof to the right-hand side of that roof, without changing the angles, I'm not walking upwards like this or something, then I know that I would have walked the length 2q, right? Because literally just this length here is 2q, and I've just shifted that length up. I haven't done anything to it. Okay, so we know that those two lengths are exactly the same. So obviously we see that thus 2p, so p plus r is equal to 2q, which implies that r is equal to 2q minus 2p. And obviously in this expression for r, that's the length of our roof ridge, there is no theta involved. So that's the first part of the question done. In the second part of the question, we want to find the volume of the attic, right? So they asked us, show that the length of the roof ridge is independent of theta. So we've done that, and find the volume of the attic. Okay, well the volume of the attic is a little bit trickier, and it relies on this sort of slicing technique. Effectively, all you need to do is slice the roof. So you can see here there's sort of a cross section of sort of the roof. Effectively, they just like take a cut from the roof at this particular point here. So if you just had like a knife and you were able to just slice the roof, you could cut it there, right? And you could cut it at the same sort of point on the other side of the triangle. So it's kind of like a symmetric cut. So I'm cutting it from sort of this length x from the left-hand side, which we know is the same as the length p from the left-hand side, and we're cutting it from a length p from the right-hand side as well. So we have this sort of symmetry, and effectively because of that, we can stick these two end pieces together after we cut them off, and we can form a triangle, and we leave behind a triangular prism. Okay, or effectively, no, sorry, a triangle, I mean a pyramid. Effectively, we have a square-based pyramid from that, and I'll get to why it's square-based, etc. And we also have a triangular prism. Did I say triangle before? I think I definitely meant square-based pyramid. Anyway, we want to find the volume of the attic. So how are we going to do that, right? That's the problem. So obviously, well, we know that we can slice these two sort of pieces off and then join them together to form a square-based pyramid and a triangular prism. So if I make a cut here, and I make a cut at the same point on the other end of the sort of roof, I'm going to, and I sort of stick those two ends together, I get a square-based pyramid and a triangular prism. But what do I actually know about those? Well, first of all, if I have a square-based pyramid, it's going to be something like this, right? One, two. Let me try and do this properly. Hold on. We got 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that was my best attempt right now at a square-based pyramid. But effectively, we know it's square-based simply because, well, this breadth is not changing, right? It's still going to be 2p, or was it 2p? Yeah, it's still going to be 2p even after, right? Like this length, obviously this breadth here is 2p, but even after I make a cut, like here, along sort of, let me just do it. Even once I make a cut along this line here, it's still going to stay the same, right? Because I'm making sort of a cut, like in a line parallel to that sort of line of length 2p, right? And so my breadth, or the length of that line is still going to be the same. It's still going to be 2p, okay? So when I remove that piece, it will still have that breadth of 2p. But this sort of length here we know is p, right? And so I'm actually going to be cutting off a piece of length p, but then I'm going to be doing that on both sides. So when I stick them together, I get a piece of length 2p. Okay, so I know that my length, therefore, will be 2p. And obviously my breadth was 2p. So this is a square as my base of the pyramid, right? So we have a square-based pyramid. And obviously that square-based pyramid, also has some height. Okay, but the height of that square-based pyramid is going to be the same, if we look back at this diagram that on the right, as the height of our attic, right? Which we already know because we figured it out in the first part to be x tan theta, which is obviously the same thing as p tan theta, right? So our height is just going to be equal to p times tan theta, right? So the first thing that we can do is we can calculate the volume of this square-based pyramid. So for those of you that don't know, the volume of a square-based pyramid, so the volume of square-based pyramid is going to be a third times the area of the base times the height, right? And if you're wondering why this is, well, it's actually quite interesting because we can take a cube and we can actually end up fitting 3 square-based pyramids within that cube, which is a pretty interesting fact. And obviously the volume of a cube is just the area of the base, so length times width, times your height. And the reason we multiply it by a third is exactly for that reason, that we can fit 3 of these square-based pyramids within 1 cube. Okay, and maybe you can look at that sort of outside of this. I won't talk about it anymore, but that's just an interesting fact. Okay, so from that, we basically have everything we need, right? Because we know that so the volume of the pyramid, so the volume of pyramid that's formed is just going to be a third times the area of the base, which we know is just 2p times 2p, or 2p squared, times the height, which we know is p tan theta, right? So when we combine all these terms together, we're going to see that we get 4/3 p cubed tan theta as our volume there. Okay, and then the next thing we need to do is we need to calculate the volume of the triangular prism, right? Because we've only calculated the volume of parts of our attic, but we've left sort of this part of the attic untouched. So we need to think about that triangular prism now. So let's do that. Let's get the triangular prism. So you just draw it out. And there are a couple of things we also know about our triangular prism as well, which I think are good to highlight after I just do this. Okay, there we go. That's fine. I don't know why I always like draw them tilted. But yeah, you can see exactly what I'm trying to say. So this is our triangular prism. And obviously, if we go back to sort of the initial diagram, we can see that effectively the length of this triangular prism is just 2q minus 2p, or r, right? Because I've literally sliced off those two end pieces that had length p. So I'm left, because effectively these two lines are parallel, I'm left with effectively a piece of um, length 2q minus 2p, which we also know it's the same as just r. We labeled it capital R at the very beginning, the length of the roof ridge that we found in the first part of the question. And so effectively we have that this length of the triangular prism, that's just r, which is 2q minus 2p. We also have that this breadth is just going to stay the same again. It's still 2p. Nothing is changing about the breadth. I'm just making a cut, but it's a parallel cut. So the length of the sort of cut that I'm making is just still going to be 2p. So that's staying as 2p. The other thing is what's the height, because we need to calculate the area to calculate the volume of the triangular prism. We need to calculate the area of the triangles on its ends, and to do that we need to find the height of the triangle. Effectively, we know that the height of the triangles on its ends is going to be the same as the height of our attic, right? Again, just literally look at the diagram. We're making the same. We're making this particular slice, but this slice that we're making isn't changing the height at all. Okay, all it's doing is changing the length, right? Because we're cutting pieces off and like, removing them from the sides. So it's going to change our length to give us 2q minus 2p, but it's not going to change our height, which means effectively that we're going to end up with this height here, which we know is the same as before. So just p tan theta. And so from that, we can now calculate the volume. So we can now calculate the volume of. So we have the volume of triangular prism. So triangle prism, which is equal to, so the area of the triangles on the end, so a half times base times height, so times 2p times p tan theta. And so that's effectively the area of the triangle on each end, right? So we have that on each end we have this triangle of area a half times base times height, and our base is 2p and our height is p tan theta, right? And then obviously we need to multiply that to find the volume of the triangular prism by 2q minus 2p, right? So we effectively multiply this by 2q minus 2p, and so we collect all those terms together and we get p squared tan theta multiplied by 2q minus 2p, right? So, I mean, you could have it as 2q p squared tan theta minus 2p cubed tan theta, right? And obviously now what we need to do, we need to just add these things together, right? So we basically just add these two volumes together. So we have the volume of the pyramid, so total volume of attic, is just the same as the volume of the pyramid plus the volume of the triangular prism, right? Which ends up just being 4/3 p cubed tan theta, right? Had 2p squared q tan theta minus 2p cubed tan theta, right? So obviously 2 is 6/3, so we can just say this is 4/3 p cubed tan theta minus 6/3 p cubed tan theta. So effectively what you get is you get 2p squared q tan theta minus 2/3 2/3 p cubed tan theta, and we can just write this as the same thing as what's it going to be, 2/3 p squared tan theta multiplied by 3q minus p, right? And that there is our volume, right? So that is that. Okay, so that's the volume part of the question done. there's only one more part of the question that we have to do, and that is we have to find the surface area of the roof, right? So you just zoom back into the question. So show the length of the roof is independent of theta, we've done that. Find the volume of the attic, we've done that. Now we need to find the surface area of the roof, and the way that we have to do that is by considering each of these four sort of plane sections, if you will. Obviously, two of them are trapeziums and two of them are triangles. So you need to find the area of each of those sort of shapes, okay? And the way that we can do that is by, again, just zooming back in on this diagram. So let me just go, all right, surface area directly under here. So we have surface area. So effectively, we can see that in our diagram, on each end, there are going to be two, there's going to be sort of one triangular, let me just rub this all out. There's going to be one triangular plane sort of roof section, right? So on each end of the roof, there's going to be one triangular plane roof section. And what we know about this already is that this length here is P, and this height here is P tan theta. Or we can even call it H, okay? But what we want to do, right, if we have these triangles, then we have that the height of these triangles is given by the hypotenuse of this triangle that we are looking at the moment, right? So if we want to find the area of the triangles on the end, because we're trying to find the surface area, and to do that we need to add together the area of these two triangles, add the area of these two trapeziums. If we want to find the area of the two triangles on the end, we need to know the height. Because we already know the sort of base length of those triangles is just 2p, but what's the height? Well, this can easily be found, so we want to consider, we consider the two triangles on either end of the roof section. Right. So effectively, we want to consider this triangle here, so it will look something like this. And that obviously that length there is 2p, but that height we don't quite know yet. We can calculate the height, so we can calculate the height by considering this triangle. Right, so it's going to be something like, so there, that's obviously theta, that's 90 degrees, that is p. So what do we already know? Well, we know that cosine of theta, we'll call this length k, we know that cosine of theta is equal to adjacent over hypotenuse, right, which is just p divided by k. So we have that this implies that k is equal to p divided by cosine theta, or which is equal to p times 1 over cos theta. And we actually have a name for 1 over cos theta, it's just sec theta. So we call that function sec theta. So 1 over cosine theta is just sec theta. It's just equal to p sec theta, right? So this length here is just p times sec theta. Okay, and that is the height of our triangle, right? So we know that this question mark thing here is just going to be p sec theta. Okay. The area of both of these, so we're going to have two copies of this exact same triangle, so we can just find the area of one and multiply it by 2 of these, is given by A triangles, just also zoom out, is given by A triangles equals a half times base, so obviously our base is 2p, times our height, which is p sec theta, obviously multiplied by 2 because we have two triangles on each, so one per end of the roof. So this just gives us 2p squared sec theta. Okay, so that's the first part of the question, but then we also need to find the area of the sort of trapezoidal roof sections, right? Because we do not know the area of these, okay? But again, because we know the angle is theta everywhere to the horizontal, we can make that exact same argument, and obviously we know this length here is p, so we can make the same argument with a triangle of sort of base p and height h and hypotenuse p sec theta, and so effectively we know that the height of this trapezium is p sec theta as well, okay? So now we consider, and we also obviously know that the length of each trapezium is given by 2q. As you can see, like this bottom length here is just 2q. So we can just use that. Right. And so effectively what we have, we also consider the two trapeziums. As shown below. Also just clocked I'm not actually showing this. As shown below, and I'm not even showing it. As shown below. So we obviously have these two trapezium sort of faces here. Kind of given up on doing this properly. Sorry about that. And so we obviously have that this length here is just going to be our 2q. This length here, which we actually also need to just r, right? If you go back to the diagram, you can see that this length up here of the trapezium, obviously the two trapeziums, they meet along that common line r. So this length here is actually a length of both of the trapeziums. It's given by r. Okay, so we have that length there is r. And we obviously have that the height of our trapezium is given by p sec theta, by the same reasoning as for the triangles. Okay, and so then we know what the area. So we have that the area of the trapezium, right? This is just a standard formula. Is just going to be a half times this length, so the bottom length plus the top length, so multiplied by 2q plus r, right? And then multiplied by the height. So the height here is p sec theta. And then obviously we can fill in what r is, because we already know what that is. R is literally just 2q minus 2p. Right, yeah, 2q minus 2p. And we multiply that by p sec theta, and so this ends up giving us a half 4q minus 2p times p sec theta, which just gives us 2q minus p multiplied by p sec theta. So that is the area of our trapezium. And obviously, though, we need to multiply this by 2, so the area of the trapeziums is this thing multiplied by 2, multiplied by 2, multiplied by 2, multiplied by 2. And so we end up just getting effectively 4q minus 2p times p sec theta as our total area of both of the trapeziums. So we have two of the exact same trapeziums on opposite sides of the roof as well. So we add these areas together to get the total surface area. We add these together to get the total surface area. Right? So effectively what we have is we have 2p squared sec theta plus 4q minus 2p lots of p sec theta. So what's that going to be? Well, this is just, we can factor out a p sec theta from both of them, and then we get, that's just going to be 2p plus 4q minus 2p. And so this effectively just gives us these two p's cancel out, so we get 4qp sec theta is the total surface area of, so that's our total surface area of the roof. Surface area of the roof. And the other expression that we had before, above here, that's the total volume of our roof. So that's the total volume of the attic. Total volume of attic. Okay, goodness me, that question is nasty. Okay, at least for a step 1 question, that's pretty involved. I wouldn't have gone for it. Obviously, you can pick your best 6. Up to what you pick. I wouldn't have gone for it, but that being said, it's a pretty satisfying one to get. And I hope you guys enjoyed the video, and I'll see you guys in the next one.